In today's note, we're going to look at intersection of lines. So this is going to focus mainly on some word scenarios, and we're going to be graphing two different relations and seeing basically what does that mean? What do those two lines tell us, and what does the intersection or the crossing of them tell us? So the problem that we're going to deal with for the main part of this lesson is that there are two amusement parks in a city. Mathemagical World charges a $20 admission fee plus an additional $2 for each ride. Radical Island charges $3 for each ride but does not charge an admission fee. Is the following statement sometimes, never, or always true? And that statement is that Radical Island is the cheapest choice. And we want to formulate a convincing argument to back up our answer. And when formulating the argument, feel free to use graphs, equations, and or tables of values to help show your reasoning. To work with a graph, if you're going to do that, and we have done that in our example, if you're working at home, go to Desmos.com. Again, we should be familiar with this. Go there, enter in the equations that we're going to come up with for each scenario, and graph them. Right? And you can take a picture of that graph, or you can keep it open in a separate window to get a general idea of what these two relations look like. But first, for the mathematical world, we need to come up with an equation. And this is going back to looking at word scenarios. But we can see that there's a $20 admission fee plus $2 for each ride. So the key thing here is this word each. Each ride means per ride, or for every ride we're adding $2. So this should indicate, right off the bat, this should indicate a multiplier. An admission fee, if you're not familiar with the term, an admission fee is basically something you pay to get in. It's a one-time fee. You don't have to pay multiple admission fees once you go or once you enter. Every time you go on the ride, they don't ask for another $20 admission fee. So this is our constant, because that $20 isn't going to change. So if I want to come up with my equation for this, y equals my multiplier, or m, so 2x, plus my constant, which is 20. So that's going to be the first equation for mathematical world. Radical Island, the only thing we see here is that it charges $3 for each ride and does not charge an admission fee. Again, we see that word each, so that should indicate a multiplier. The admission charge, or the fact that they don't include an admission charge, talks to us about the constant. So if I'm coming up with an equation, y equals the multiplier 3x, and in this case, no constant or no admission fee, so I could do plus 0, or just to make it easier, I don't have to even show it. So these are going to be the two equations that you're going to graph. So pause the video, go to Desmos, enter these two equations into separate lines, and graph them, and hopefully what you get is something like this. So these are your two graphs. Again, just as a reminder, the equation for the one was y equals 2x plus 20, and the other one was y equals 3x. If you're working on Desmos, usually when you hover over them, you should see kind of a gray dot come up. If you click, it will give you the actual coordinates of that, and they usually only show key coordinates. Now, the one thing I want to do is I am only concerned about everything before or after the y-axis. And the reason that I'm doing this, so we scratched out all negative x values. So anything that was after 0 we scratched out, and the reason for that is that these values do not make sense in the scenario. And basically what that means is, if I was looking at a point over here, that would be if I went on say negative 5 rides. It doesn't really make sense in terms of the scenario. I can't go on negative rides, right? Usually that would probably mean that if I go to the fair or to go to the amusement park and say, oh, I don't go on these rides, now you need to give me money, that doesn't really make sense. So the reason I scratch them out is because I don't want to look at them, and I don't want to get confused by them. Basically, they don't have any information that will be important to me for this scenario. They're still there, they're still viable points because we know lines continue on forever, but in terms of the scenario, I don't need to focus on them. So again, the solution for this was which statement is sometimes, always, or never true, and that is that Radical Island is the cheapest choice. So looking at this, actually this is Ri, this is MW, so again, I'm trying to figure out, is Radical Island the cheapest option? So looking at this, there are 3 scenarios that I can look at. And the 3 scenarios that I'm going to look at are this value here, we'll call this number 2, this scenario here, or these values, and then finally these values over here. So we'll call this the 3rd section. So there's 3 different sections that we're going to be looking at to help us come up with our solution. So looking at the first solution, if I look at these 2 lines here, everything in red, or in this red box, I can see that Ri, or the blue line, is the cheaper option. You can tell because it's the lower line. We know our y-axis is dealing with money, our x is dealing with number of rides. So the lower the line, the less money there is. So in this case, Ri is the cheapest option. Cheapest option. Again, you can say, well, because the y values are lower, it's the lower line, whichever one you want to say. So it is the cheapest option. In section 2, or this point specifically here, they meet at a certain point, or they cross or intersect at a point. So what that means is that they cost the same for 20 rides. So they cost the same for 20 rides, which in this case is $60. So they cost the same at point 2. In the 3rd section, so everything after point 2, Radical Island is more expensive and we see that because the line is higher. So Radical Island is more expensive, line is higher or above Mathemagical World. We can use the same option or same reasoning for the first one. So RI is the cheapest option. Line is lower or below Mathemagical World. So that same reasoning applies in the opposite. So it's the cheapest option because it's below. It's the more expensive line because it's higher. So in this case, going back to that original question, of that sometimes always never statement, using these three options, we can make the statement, or we can make the assumption that the statement is only sometimes true. And again, that statement was that Radical Island is the cheapest choice, but we see that's only sometimes true. In this first scenario, or first section of our graph, it's definitely true. At this green point, or at this intersection point, it's not true because they cost the same. And then after that green point or intersection, it's not true because it is more expensive, or it's the higher line. So that's how we can get that solution, by looking at the graph. Our next option, if we're looking at a table of values. So again, we have Ri, which was y equals 3x, and we have Mw, which was y equals 2x plus 20. We can create a table of values and compare them and see if it's always higher, always lower, sometimes higher, sometimes lower, or the same. So we know that it is $2 or $20 to start, and then as we increase the number of visits or rides, it's $5 or 5, and then we multiply that by 2, so it's increasing by 10, 30, 40, 50, 60, 70, 80. For Radical Island, there's a 0 initial fee, and we're increasing by 3 every time, so it increases by 15. So 15, 30, 45, 60, 75, 90. And even looking at this table of values, we can still see the same thing. There's those 3 sections of information or scenarios. So looking at the first one, again, we see the same thing. Radical Island is cheaper. We see that there is that one scenario where they are the same. So the second scenario, or possibility, they cost the same. And that third option, or possibility, we can see that Radical Island is more expensive. So again, using the tables of values, we can use our equations or even the scenario to fill in the table of values and see that there is a scenario where it is sometimes it's cheaper, where it costs the same, and where it's more expensive. So again, it confirms that statement is only sometimes true. If we're looking at the equations, this one is going to be a little bit more difficult. But again, if we look at Mathemagical World, y equals 2x plus 20. And if we look at Radical Island, which was y equals 3x, there's a couple of takeaways from this. So first, Radical Island does not have an initial value. So because it doesn't have an initial value, there is going to be a certain point of time or a certain number of visits or rides where it is going to be cheaper because you don't have to pay that upfront fee. So Radical Island does not have a constant, or in this scenario, an admission fee, does not have a constant, So it will be cheaper at the start. Now, you may be thinking, well, how do I know that it's not going to stay cheaper the entire time? And the reason for that is by looking at the multiplier. Radical Island has a higher multiplier. It has a multiplier of 3, or a rate of change of 3, compared to Mathemagical World that has a rate of change of 2. Because Radical Island has a larger multiplier, we know, or we should be able to assume, that eventually at some point it's going to outpace Mathemagical World. So RI, or Radical Island, has a higher multiplier. Therefore, it will eventually be more expensive. So right from there, even though we don't know based on the two equations by looking at them when they're going to cost the same, we can still confirm our statement is only going to be sometimes true, because we can already tell that it will be cheaper at the start, but eventually it's going to become higher or more expensive. And again, that is enough to confirm that statement. So in conclusion, again, the original problem was, is the following statement sometimes, always, or never true? And that statement was, Radical Island is the cheapest choice. After looking at all those different scenarios, the graph, the table of values, the equation, basically all those methods confirm that our answer is that the statement is only true sometimes. And again, there were 3 different cases that we came across, or 3 different scenarios or situations. One was that at exactly 20 visits to the park, both places cost $60. So basically, either option you choose, either park, it's the same price. The next scenario or case was that if you have under 20 visits, Radical Island is the cheapest choice. Again, that goes back to the fact that it doesn't have a constant. It didn't have an admission fee. And then Mathemagical World is cheapest when you're going over 20 visits. And that's because it has a lower multiplier or rate of change. So eventually, the higher price per visit for Radical Island will overtake the cost of Mathemagical World. And we know that's after those 20 visits. So again, there are 3 different scenarios or 3 different cases that we have to look at, and they're not all the same, which is why our statement is only sometimes true. So as a summary, when working through 2 different lines or 2 different linear relations, the solution to the lines is considered to be the point where the lines meet. And that's basically saying that at that point, or at a certain x value, the y values will be the same. And another term for this, and you'll learn more about this in grade 10, but this is called the point of intersection. Where do they cross? And then working with a contextual problem or a word scenario like the amusement park one we just looked at, the conclusions we draw come in 3 parts. The first part is where the values for both the scenarios are the same. Again, this is the point of intersection, where they cross. A part is where the values of line 1 are lower and the values of line 2 are higher. And the third part is when the values of line 1 are higher and the value in line 2 are lower. So when we write a conclusion to a contextual or word problem of this type, or of these scenarios, we must talk about all 3 parts of the conclusion. So again, talking about when they're the same, when one is higher, when one is lower. Those are the three scenarios that we have to talk about. Let's look at another example. So Rosie is touring a city. She has found a company that rents bicycles and rollerblades. The company charges an initial fee for the rental or for the equipment rental, and then an additional cost per hour of rental. The linear relationship between cost and rental time for both the bicycle and rollerblades are shown. Determine the conditions under which each option is the most cost effective, or basically cheapest. So we see the bicycle in red, or the solid line, and we see rollerblades in blue or dotted lines. We can see clearly on the graph it does give us this nice intersection point of 4:15. So right off the bat, actually let me keep it color coded the same. So we have our green to represent our point of intersection, or our middle point. We use red to highlight anything before that, and we use the one blue to highlight anything after that. So in our one scenario, or in red, the blue line or the dotted line is lower. We can see that clearly. Then it's lower than the red line, so we can say rollerblades are cheaper for rentals less than 4 hours. And the reason I said 4 hours is because I know that at 4 hours, they're going to be the same cost, and then we kind of switch cases. So the rollerblades are going to be cheaper for rentals less than 4 hours. For my middle scenario, or the point of intersection, both cost the same amount for 4 hours of renting. So that's that point of intersection or solution. And then lastly, the third part, or third case, is that the bicycle is cheaper for rentals longer or more than 4 hours. So again, those are three scenarios. One dealing with the situation before we get to the point of intersection, the point of intersection itself, and then one after the point of intersection. So again, those are our three scenarios. Again, similar to that word problem, or the amusement park one that we just talked about. In the second example, this one is just looking at two equations in general. We want to determine graphically the point of intersection or solution of the two lines. So if you didn't have the graph, you can plot the graph or graph it. You can enter it into Desmos, and you should get something like this. And what you would see here, where they cross, is already nicely labeled for you, or if it wasn't, you should be able to see where they cross. So here, all it's asking for is the solution. So the solution is 2 and 6. Or you could say the point of intersection is 2, 6. There's no word scenario to it, so we don't really have to go any further than that. Example 3, two lines are parallel. What is the point of intersection or solution of the lines? So this one you have to think about. Let's say we come up with two equations, y equals 3x plus 11. Remember, because they're parallel, they're going to have the same slope. Let's say plus 10. So if we wanted to roughly graph that, oops. So let's say that's one line, and just above it is the next one. What's the point of intersection? Well, we should know from parallel lines that they never cross. So there is no solution to these lines. Basically, they never cross. So parallel lines won't have a solution because they never cross. And again, this is just an example of, or these were just examples of looking at when we're graphing two linear relations, and understanding what it means when they cross, and just again understanding the different cases that occur before that point of intersection or where they cross, and then after the point of intersection, or after they cross. And then hopefully we should be able to apply this understanding to word scenarios or contextual questions to understand or come up with solutions.